My name is Kate, and I am a scientific content writer for Izon. Today, I'm going to be talking to you about which anticoagulant you should be using for your extracellular vesicle research. With blood samples being perhaps our most go-to sample for diagnostics, it's of no surprise that blood is the most popular biofluid for extracellular vesicle isolation. Deciding to choose blood as your starting biofluid next brings you to the all-important choice of serum versus plasma. Which should you collect, and what impact will that have on your isolated EVs? During the clotting process, to create serum, activated platelets release an overwhelming amount of EVs, swamping any non-platelet EVs in your sample. As you can see here, the concentration of EVs in serum is around 3 orders of magnitude higher than it is in plasma. This makes serum a great source of platelet EVs, yet a relatively poor source of non-platelet EVs. With serum EVs, you're not looking for something which resembles the EVs in situ in a patient's circulation, rather something which was mostly created ex vivo. This is especially important when searching for biomarkers or creating a diagnostic test, as any disease biomarkers are likely to be lost in the sea of platelet markers. For most applications then, plasma will be the preferable choice. Even when choosing plasma, there are other factors which could cause platelet activation, and may result in large-scale secretion of platelet EVs. The first is the blood sampling process itself, which necessitates injury and pressure, both of which will cause some platelet activation. To combat this, the first 1 to 3 mL of blood drawn can be discarded. Transporting samples can also cause platelet activation by inducing shear stress, so minimizing the tube inversion and transportation is important. Next, whilst anticoagulants will inhibit clotting, this process is not a perfect inhibition, which makes long wait times before processing a contributor to platelet EV formation. Lastly, hemolyzed samples should be avoided as cell fragments will contaminate the EV isolate. But let's rewind. If you want to use plasma, first you need to pick which tubes, and so which anticoagulant, to put your sample into. If it was a matter of what is the most popular, then EDTA would win hands down. But is that because it's better, or because it's more of an active habit than a conscious decision for EV quality? First, let's take a look at size. Here we have taken data from 9 studies to determine whether the size of EVs isolated differs based on which anticoagulant was used, regardless of the isolation method. As you can see, there is no impact of anticoagulant type on the size of EVs isolated. This means that size should not be a factor when you are choosing your anticoagulant. Then what is? One of the biggest considerations for plasma EV studies is ensuring that the EVs you end up isolating match those in the circulation before you took your sample. For this, citrate-based anticoagulants come out on top. Both heparin and EDTA result in the generation of additional EVs from cells such as myeloid cells and platelets, as compared to citrate-based anticoagulants, which may skew the results of both functional and biomarker studies. This is only true when processing within 1 hour of taking blood, as further delays can result in EV production by a variety of cell types within the sample, the profile of which differs with anticoagulant type. As such, prompt processing should always be prioritized for EV studies. As mentioned above, transportation also causes EV generation. EDTA has been found to perform particularly poorly when samples are transported at room temperature. Transporting EDTA plasma at room temperature results in a large increase in EV number, with flow cytometry profiling of these EVs suggesting that they will likely come from a variety of cells. It is worth noting that transporting at higher temperatures, such as 37 degrees Celsius, caused an increase in EVs from plasma using all anticoagulants, though that in EDTA plasma was lowest. This could make EDTA a better choice for plasma sampling and transportation in high ambient temperatures, and citrate-based the best choice for temperatures lower than this. Storage can also impact upon EV composition from plasma samples. For this, citrate-based anticoagulants perform best over multiple freeze-thaw cycles. This could be particularly important when storing your isolated EVs in a location where consistent power supply is not guaranteed. If RNA analysis is on the cards, heparin is also your worst bet. Whilst all anticoagulants may impair polymerase chain reaction technology, heparin has been shown across multiple studies to have the biggest inhibitory effect. Unfortunately, there has been no comprehensive comparison of the impact of different anticoagulants on proteomics, metabolomics, or lipidomics of EVs. However, as citrate-based anticoagulants perform best when it comes to preventing EV generation ex vivo, it follows that citrate-based anticoagulants should be used for omics and biomarker studies. Finally, when functionality of your EVs is important, stay away from heparin. This is because heparin sticks to EVs, inhibiting their uptake into target cells. This makes heparin an unpopular choice for EV studies. Current literature on the topic therefore suggests that citrate-based anticoagulants are the most preferable for EV studies. However, this may not always be possible, especially when working with biobanked samples. The choice of anticoagulant may not always be in your hands. Whichever anticoagulant you choose, the most important thing is to be aware of the limitations surrounding it. For more information on plasma EVs, see the links down below. Thanks for watching.